Today we're going to go ahead and run our KinTek test reaction on this system. We're going to go through from start to finish, including setting up the light source and powering the system on from everything turned off, the exception of the computer, as you can see. So the first thing that you want to do is either bring up the drive box for the system or bring up the computer. The order of those two doesn't matter. What matters is when you bring up the software itself. You want to make sure that the drive box is powered on and that you have power to the system before turning on the software. Otherwise the software will error out and you'll just have to restart it. Won't hurt anything, but now to explain the components of the system, we have our drive box here that controls the motor that is on the motor stand. And then we have our detectors, PMT1, PMT2, and PMT3. And we have our syringe chamber. So these are all components that when contacting us, you have a problem with one of the components, we may ask you about one of these components, referring to them by these names. So first, I want to point out we have a component here on an SF-300X that is the stop valve to the system. This valve allows solution to pass through when the motor pushes solutions through. When you turn on the drive box, you will hear and or feel a click from the stop valve because it will energize the stop valve and then de-energize it. So it should click twice when you power on your drive box. If it doesn't, we'll need to pay attention to checking this valve to make sure it's operating properly. If this valve doesn't operate properly, you could do immediate damage to the system. It will need to be sent back and repaired. When I powered on the drive box here, I heard the stop valve click, so we know our stop valve at least is receiving the signal to open and close. Now that the system's powered up, I can bring up the KinTek stop flow data collection software. And the first thing that we'll want to do is check this stop valve. Make sure that when we click valve closed and valve open, that we hear and feel the valve operating. I'm going to collect on all three channels. As you can see, we have fluorescence A and absorbance C up currently. So I'm going to turn the display for PMT2 on, and I'm also going to turn on collection for PMT2. Under data collection, for this particular reaction, we want our T1 time point to be 0.05 seconds, and we're collecting 2,000 points per trace. Next, I'm going to go through the filters for the PMTs. For this particular reaction, we use a 320 nanometer long pass filter. With our fluorophore of tryptophan, it excites at 280 nanometers and it emits at 348 nanometers. So the 320 nanometer filter blocks the excitation wavelength, so all we see in PMT1 is the 348 nanometer excitation. In order to change these filters, you will take a small flathead screwdriver there's a filter retainer that has a groove that you insert the tip of the screwdriver into the groove and pry the filter retainer out. This is nothing more than a piece of plastic with an O-ring. The filter itself can then be installed. Right now the filter it's inside the unit, but these filters can be installed without even actually touching the filter. And then you place the filter retainer back in place, using care not to actually touch the filter when you press the filter retainer in place. Replace the filter holder into the system. Now, as you'll notice, I have no PMT high voltage on any of my PMTs currently. I set up my filter system before powering up any of the PMTs because if ambient light is allowed to pass through and into these PMTs while they're powered up, it's devastating. Within seconds, these PMTs will burn out and they'll need to be replaced. So you want to make sure that you have no voltage on any PMT that you're removing filter holders. Very important. Now that I've got my filters in place, PMT2, we're going to be collecting data unfiltered. But now that I have my filters in place, we can begin flushing the system, and then we'll go into the light source. The easiest way to flush the system is to do it manually, rather than allowing the motor to push the solutions back and forth. And there's a few reasons that I flush the systems manually, other than just speed. We want to make sure we get all of the air out of the drive syringe and fill the syringes with water. And you want to flush at least 3 times each time to ensure that you have a flushed system prior to any collection. This particular reaction is a single mix reaction, so we will only be using syringes A and C. The only time syringe B will be filled is if you are doing a double mix reaction. Here, opposite the load fire valve, we have the double mix valve. This double mix valve should be in the horizontal position, thus blocking any flow from syringe B down through the system. If the double mix valve is in the vertical position, as shown, that means there is a passage from syringe B down through the system. For this particular reaction, that valve should be in the horizontal position, thus closing that path. Now that I have my syringes full of distilled water and my load fire valve is in load, I can go ahead and manually open the stop valve with the software, grab the syringe plungers, and push down. Solution then flows through the system and into the waste syringe. This should be done at least 3 times. Doing this manually also is an easy method of checking the operation of your stop valve. If you use the motor platform to push solutions through and the stop valve isn't operating properly, this motor is strong enough that it's going to push solution out anywhere if this valve is not working, and it will damage the system. So in light of that, I encourage users to push these syringes down manually. If the stop valve isn't working properly, you're not going to be able to push solution through, and then you can start investigating and determine why. So that was 2 full flushes. And there's the 3rd. Ensure to keep an eye on your waste syringe. Make sure it doesn't overflow. Otherwise, there will be a mess on the floor. Now that we've flushed the system, I'm going to load distilled water in syringe C and our fluorophore in syringe A. This will allow me to push our fluorophore through the system and into the cell so that it can be excited by the light source so that we can set our PMT levels for collecting data. And once again, you want to make sure that there is no air in the drive syringes. Even small bubbles should be eradicated. You eradicate the bubbles by pushing in from the load port slowly and then evacuating out of the drive syringe quickly. And it's a back and forth motion that you'll become familiar with after a very short time of using the stop flow. And once you can verify that there are no bubbles at the tips of the plungers, obviously air goes up. Sometimes it will stick down at the bottom, but usually it goes up. You can make sure you have no bubbles in the drive syringes. You're ready to go. So now we have tryptophan in syringe A and distilled water in syringe C. With the system still in load, with the load fire valve still in the load position, I'm going to push the drive plate down until I'm sure that both syringe plungers are engaged with the drive plate. If they're uneven in any way, there's a chance that you could get interaction from one syringe through the cell and up into the other syringe. So, with the stop valve or the load fire valve still in load, we will push down until we see movement in both load port syringes. That ensures that your drive plate is against both of your drive syringes. Now that we have that, we can switch back to fire on our load fire valve and actually push some of our fluorophore and water through the system in order to prime it. Once we've got the system primed, now we're ready to turn on the light source. This is an LED light source, so it's rather easy to operate. Right now this has a UV LED in place, so on this particular controller you'll get a UV LED warning. You can tell it OK, and then we power on the controller, and here we have our our level of current that is controlling the LED itself. Anywhere from 10 to 30% power should be sufficient for most fluorophores. Our fluorophore, we can actually go, because our fluorophore is so highly concentrated, we can actually go down as low as 1, 2, or 3% sometimes, depending on the experiment we're doing. In order to determine that level, at this point we can go ahead and we can set our PMTs. We have light coming into the cell, our filters are in place, and we have our fluorophore loaded. Entering a value in the PMT high voltage field, we'll turn on the PMT, and right now it's saturated, so we want to step down in 50 volt increments and give it a few seconds between changes to settle. And there we go, we're very close to mid-range on our scale, which is where you want to be for this particular reaction. Now, because PMT2 is unfiltered, it may require a little more voltage, or I'm sorry, a little less voltage. Now, right now, our LED light source is set to 15%. I have a PMT high voltage of 400 for PMT1, 325 for PMT2, and 394 for PMT3. Now, for all three of these values, that's on the low side. PMTs 1 and 2, their level of stability comes in at about 350, PMT high voltage of 350. PMT3, on the other hand, their level of stability comes in at about 400. So we have, in PMT2, we have a PMT high voltage of 325, which is a little under our 350 volt low number. So in order to remedy that, we're going to reduce the amount of light coming into the system by reducing the current flow through the LED. Easiest way to determine the correct level is if we set our PMT high voltages to our desired levels and then adjust the LED accordingly. So now with our PMT high voltage levels set at 450, 410, and 425, I go up incrementally until I reach about mid-scale for all three channels. PMT1 here is still a little under, PMT3 is still a little under, PMT2 is a little over. So I'm going to raise the PMT high voltage levels of 1 and 3 in order to get those to mid-scale. So that's mid-scale for all three levels. We're at a current level of 3% on our LED. And our PMTs should be relatively stable. Now, as I collect data, there may be bubbles in the cell, there may be impurities in the cell, things like that. These levels may change after data collection goes through. And you can make adjustments. As you can see, in our unfiltered channel, we had some impurities going through the cell. They do not show up in our filtered channel because they're actually reflections rather than reactions. The filtered channel, all of these reflections are filtered out. Now, as we can see, PMT2, we're a little under once again, under our middle. So we can bump up our high voltage a little bit and get rid of any instability that might occur. Much better. Now we can go with a new file and collect a few more shots to make sure our signals overlay each other and our signals are flat. With each group of collections, you may get a trace or two that are outlying. So we delete those and continue on. So now with our PMT levels set and our reference data collected, we can go ahead and set our dark currents on our reference for the absorbance channel. In order to set our dark current, we turn off our LED source and click the Set Dark button. Some LED controllers have an auto shutter feature that you don't actually have to turn the source on and off to do this. It will do it itself. So then we turn our source back on and read our reference. Notice each channel has its own set of dark current and reference buttons, but you only have to click on one of them and the system will read all three channels.